Hi, I'm Jim. At ReleaseTEAM, we favor outcomes before tools. We provide DevOps consulting, CI/CD implementation, platform support, training, and software solutions for enterprise and regulated environments. Whether you need strategy, execution, or the right tooling in place, we help you build delivery systems that perform. Welcome to the channel. GitLab can leverage a variety of runner designs, each with different advantages and costs. In this presentation, I'll go over the different GitLab runner designs and some best practices to mature your CI/CD pipelines. Different CI/CD platforms use different terminology for the component that executes the steps of a CI/CD process. GitLab uses the term runner for the code that is installed to execute process steps. Regardless of which runner you're using, they all communicate with the GitLab server to be assigned work. While it's possible to host a runner on the same system as the GitLab server, it is only appropriate for small lab environments and is not recommended for production installations. Think of an executor as a type of runner. Executors all perform the same function, but the different underlying technologies have advantages and disadvantages. Keep your overall goals in the back of your mind, and consider the trade-offs between performance and pricing as we go through the different types. Here you can see a summary of the different executors and when to use them. Not included in this table is the custom executor, which is a flexible framework for defining your own behaviors for running jobs. I'll talk about the custom executor more later. The shell executor is not recommended for most cases, but is useful in some special situations. Think of a shell executor as running a shell command on a remote host. The shell executor simply runs commands on the runner host. The lack of job isolation makes this runner type dangerous, particularly for public projects, because forks of a public project can create a pull request that triggers a workflow running untrusted code on your machine. Because the shell executor has no isolation, the runner can be poisoned to affect future jobs. While not preferred, there are some specific situations where the shell executor is appropriate. A shell executor can be a quick solution for trivial jobs, like triggering a webhook to send a Slack message. The shell executor requires that the host be able to run the GitLab agent on the system. For situations where you can't run the agent, use the SSH executor, which we'll get to later. Because of the dependency and cleanup risks of shell executors, we suggest only routinely using them for jobs that can execute without access to source code. If your situation suits a shell executor, be very careful with how you implement the job so that it cleans up after itself correctly when the job is successful and when it fails. Shell commands can exit for a variety of reasons, such as different operating system signals. Be sure that your job recognizes the different states and reacts correctly. To reiterate, don't use any executor with minimal job isolation, like the shell executor, with public projects. The core issue is not a bug within GitLab, but a structural risk inherent to all CI/CD platforms, potentially allowing untrusted users to execute code on your private infrastructure. The shell executor is a powerful tool in the right circumstances, but use it cautiously. Unlike the shell executor, the Docker executor has very strong job isolation, making it a better choice for general-purpose workloads. Once configured, Docker executors are the industry standard for isolation and ease of use. If you've ever dealt with a shell executor where one build breaks another because they share the same global dependencies, you know the pain of environmental drift. The Docker executor solves this by spinning up a fresh container for every single job. Here is why it's become the industry standard for CI/CD pipelines. With the Docker executor, every job starts with a pristine environment. Since the container is destroyed after the job finishes, there is no residue left behind. If a build process fails or runs a broken script, the next job runs in a pristine environment. Build environments are defined in your repository via a Docker file or an image name in your CI config. so different environments are easy to configure and deploy repeatably. The same image used in CI can be run locally by a developer. If it works on their machine, it will work in the pipeline. The privilege mode trap is a common security pitfall in CI/CD environments where a user grants a container privilege status to perform specific tasks, like building Docker images inside a Docker container, Docker and Docker, but inadvertently gives a container full root access to the host machine's kernel. Because containers share resources on the host machine and fully initialize the build environments for every job, pipelines can perform poorly if the host is overloaded. The Docker Executor is the industry standard and is usually a good choice for general-purpose runners. There are some specialized situations where using a Docker Executor is specifically the right choice, such as requiring several build environments and services for testing. The Kubernetes Executor follows a manager-worker pattern. A persistent runner manager, typically installed via Helm, pulls GitLab for jobs. When a job is assigned, the manager communicates with the Kubernetes API to spin up a job-specific pod. Choosing between the Kubernetes Executor and the Docker Executor usually comes down to a choice between individual machine performance and cluster-wide scalability. Both use containers to provide clean build environments. While the Docker runner is limited to the resources, CPU/RAM, of a single host. If you have 100 jobs, but your VM only has 16 gigabytes of RAM, 90 jobs will sit in a pending state. Kubernetes leverages an entire cluster. It can distribute 100 jobs across dozens of nodes. If the cluster runs out of space, features like Cluster Autoscaler can automatically provision new nodes to meet the demand. Kubernetes executors allow for transparent scaling, high availability, and native integration with cloud providers such as Google Kubernetes Engine, Amazon Elastic Kubernetes Services, and Azure Kubernetes Service. The Kubernetes Executor encourages using Kaneko or Builda to build images without root privileges, which is a significant security upgrade. Similar to Docker, Kubernetes runners operate in a shared environment. If job pods aren't strictly capped, they can trigger cluster-wide instability, such as memory and disk shortages. Kubernetes jobs require a full pod lifecycle. This adds up to 30 seconds of overhead for the job, compared to Shell or Docker executors. If the runner manager pod crashes or is killed abruptly, it may leave zombie job pods running in the cluster that never get cleaned up. If you have a small team, a single project, or require extremely low latency instant start builds, since Kubernetes pod orchestration adds a few seconds of overhead, the Docker Executor is often simpler and faster to maintain. If you're running your workers in the cloud, the Instance Executor provides maximum job isolation by using a new virtual machine for every job. It is the modern equivalent of the Shell Executor, but with the ability to scale. The Instance and Autoscaler Executor follows the manager-worker pattern, similar to the Kubernetes Executor. The runner manager provisions a VM from a cloud provider. The job script is then executed over SSH on that host. Direct SSH access on port 22 is required for the runner manager to communicate with the worker instances. For simplicity's sake, place the runner manager in the same network as the runners. While appropriate for any workload, the Instance Executor is particularly useful for mobile development that requires emulators or low-level hardware and kernel access for driver development. Instances launch more slowly than a container and may be more expensive to run. Maintaining golden images will require a CI/CD workflow of its own. Periodically build images with automated tools like Packer or EC2 Image Builder with up-to-date and approved packages. As part of the build, generate a software bill of materials from the AMI and import it into GitLab's dependency scanning system. While GitLab's native container scanning is designed for Docker images, you can achieve the same result for AMIs by using an external scanner to produce an SBOM and then providing that report to GitLab. After the build runs, the packages found in the AMI will appear in the dependency list, just like container dependencies. The SSH Executor allows GitLab Runner to execute commands on a remote machine. Unlike the Docker or Kubernetes executors, which create ephemeral environments, the SSH Executor connects to a pre-existing, persistent external server over the SSH protocol. The SSH Executor is intended for legacy systems, specialized hardware, or environments where the GitLab agent cannot be installed. SSH is a well-known, widely supported secure protocol for communicating between systems and is the communication channel for other executors, such as the instance executor. This executor is appropriate if your build needs to run commands on a specialized physical system. Don't be put off by descriptions of the SSH Executor as the tool of last resort. This is a powerful solution when there are no other good choices. We most frequently see this executor used for testing built artifacts on native hardware. Where possible, manage the remote host as code with a configuration management tool such as Ansible and automatically propagate changes such as rotated SSH keys to GitLab secrets. When you run a job on an SSH runner, the commands in the script block are written to a temporary file, then uploaded to the remote server, where they are run. To minimize the risk of polluting the runner environment, when writing any script block, but especially when those jobs are run in persistent environments, program defensively. Set the shell flags to exit on errors, unset variables, and errors in pipe commands. Also, use the bash trap command for the script to clean up after itself on exit. For advanced configurations, the custom executor is a toolkit for building GitLab runners. Environment setup and job execution are managed by your own external scripts called drivers. In this example, you can see the definition of various scripts that are executed in order: config, prepare, run, cleanup, to perform tasks like starting a local VM, running commands within the VM, and destroying the VM when the job is complete. Note that you have to manage and install the driver files separately from using them in a custom executor. You should develop and deploy the driver files in their own CD project. Similar to code run via script or SSH executors, program defensively when implementing drivers. Unlike Docker executors, a custom executor using libvirt can be configured to support direct access to the underlying hardware. This is vital for processes that require access to USB or PCI devices, while still running the processes in an ephemeral environment. There is an existing open-source libvirt driver on GitLab.com. Another example of using a custom executor is integrating with AWS Fargate, which is a serverless, pay-as-you-go compute engine for containers that works with Amazon Elastic Container Service, ESC, and Amazon Elastic Kubernetes Service, EKS, eliminating the need to manage underlying EC2 server infrastructure. Fargate is a serverless compute engine for containerized applications, compatible with both ECS and EKS. Users package applications in containers, define CPU/memory requirements, and Fargate runs them. Fargate offers high-performance scaling based on advanced algorithms like target tracking, step scaling, and predictive scaling to manage demand. This eliminates the need to provision, configure, or scale clusters of virtual machines to provide compute capacity. The interface between GitLab and AWS Fargate is a GitLab runner. We're describing a dedicated runner here, but a labeled existing runner will work. In a standard fixed configuration, the task definition typically has a hard-coded container image. In a fixed setup, every job, regardless of what is in the .gitlabci.yml, runs in an identical environment. To allow different images for every job, you have two ways to handle different images. 1. Create multiple ECS task definitions and specify the Fargate_task_definition variable in your gitlabci.yml file. 2. Register multiple GitLab runners on the runner manager, each pointing to a different task definition file. Tag the runners to reflect the different task definitions. Fargate is ideal for workloads where you need an elastic amount of capacity with very large limits. One example could be scheduled nightly builds. Fargate has the advantages of a Docker Executor without the need for maintaining your own Docker hosts. With the benefits of Fargate, there are some shortcomings. Without support for privileged mode, you cannot run Docker within Docker, often necessary for siege systems to build and manage Docker image files. Similarly, USB and GPU devices are not natively available from within the container. Here are some of the patterns that have led to success for our clients. Remember, GitLab is a sophisticated system that solves a sophisticated problem. Sometimes it takes a good deal of work to take your environment to the next level of maturity. Struggling with where to start? Start with a small Docker environment, but slightly larger than you think you need. Monitor that environment and decide if you need to scale up. Scaling up can involve adding more Docker hosts or moving to a Kubernetes environment. If you already have Kubernetes configured, try to leverage the existing deployment. If you have specific needs to move to instances within AWS, that is an easy way to efficiently scale for very large capacity spikes without overspending. Different types of executors have different advantages and disadvantages, depending on the needs of the job. For example, a collection of Docker executors is useful for smaller utility jobs like triggering webhooks or analyzing code for code quality and security flaws, without utilizing more powerful build systems. Disable run untagged jobs for specialized runners, e.g., Windows, GPU, or Apple Silicon. This prevents generic Linux jobs from accidentally landing on expensive or incompatible hardware and failing. In GitLab CI/CD, runner tags are the primary mechanism for routing jobs to the specific infrastructure they require. Adhering to best practices ensures your CI/CD fleet is scalable, maintainable, and cost-effective. Instead of generic names, use a structured naming convention that describes the environment or hardware. Hard-coding project names into runner tags creates maintenance debt. If a project moves or scales, you are forced to update both the runner and the .gitlabci.yml. Instead, use capability tags like high memory and assign that runner to the project or group. From a security standpoint, self-hosted runners can present security risks. The most critical concern is a malicious job breaking out of its intended environment to compromise the host machine. The shell executor provides virtually no isolation. Runners handle sensitive data, including API keys, SSH keys, and the CI_JAWA_ token. If you use a static runner, artifacts or temporary files from a previous job may persist on the disk. A subsequent job from a different project could scrape these files to find secrets. A runner is a bridge between your code and your infrastructure. If a runner is compromised, it can be used as a jump box to attack internal services. Ensure your runners have high IOPS disks. Siege CD is extremely write-heavy. Slow disks often become the primary bottleneck for job speed. For massive repositories, use the fetch Git strategy or set Git depth to avoid downloading the entire history of the project for every single job. For performance optimization, use an S3 compatible bucket for caching. This allows different runners to share the cache, significantly speeding up npm install or Maven compile steps across your fleet. Thank you for watching. If you found this overview of GitLab and CMMC helpful, be sure to like the video and subscribe to the channel for more insights on DevSecOps, compliance, and secure software delivery. If you have questions about implementing GitLab in a CMMC-aligned environment or need help navigating compliance requirements, reach out to us at ReleaseTEAM. We're here to help you build secure, compliant, and efficient pipelines. See you in the next video.